so this week we're going to take a look at vectors. So vectors are something that if you take physics or other classes, you might study a lot of vectors and do applications. We don't do as much application. All right, we're just going to learn a little bit about what they are, what they're used for, and we're going to do some sketching today. And then later on, we're going to get away from sketching, and I'll explain why. So a vector is basically used when you want to model something that has what's called a magnitude and a direction. An example would be velocity. Velocity is not just how fast something's going, okay, that's magnitude, but it's also which way is it going. So if you wanted to describe, like let's say an airplane, the velocity of the airplane, you'd have to tell me how fast it's going, and then you'd also have to tell me the direction. So you could say like 500 miles an hour east. That's the velocity. 500 is the magnitude. East is the direction. Another example of something you could use a vector for is force. Okay, so force, the magnitude of the force would be like how hard you're pushing on something. And the direction is which way. There's a difference between pulling up on something versus pushing down on something. So to fully describe the force, I need to know which way the object is being pushed or pulled on and how hard. Okay. So vectors are perfect for that because they describe both things at the same time. Yes?
So in physics we learned about this, but what's the one that doesn't have direction?
Something that doesn't have a direction?
Yes, like a quantity with no direction.
Maybe like a scalar?
Yes, that's what it is, vector
Yeah.
scalar.
Yep. So the easiest way that you can draw a vector is with an arrow. Because an arrow has an arrowhead on it, it naturally tells you which way it's pointing. What do you think we could do to the arrow to show magnitude?
But isn't it array?
Yeah, array and arrow.
Oh, it's the same thing?
Yeah.
I thought array was like when an angle doesn't have like it's only array.
So array is just an arrow.
Oh.
Yeah. Goes in one direction.
Interesting.
But what do you think we could do to represent magnitude?
Pointing up arrow.
What's that?
Arrow pointing up.
Well, if it points up, that's the direction. So the way that the tip of the arrow points is the direction.
Maybe like have the bottom be flat and then it goes up. I don't know.
But how do you think, like, if you had like a plane traveling east at 100 miles an hour, and then a plane traveling east at 200 miles an hour?
You put the
Opposite side.
So what could we do with the arrow?
You could put an arrow on both sides.
Flip it and make the arrow point.
Well, if they're both going east, the arrows have to point to the right. But how would you represent the faster plane?
With a parallel.
A bigger
longer
line.
Arrow.
What do you
A
mean
shorter
bigger?
arrow.
Like
Could you
a
just
long
faster one.
like arrow here,
Yeah.
arrow here, but one
So
short.
longer or shorter?
Yeah.
Yeah. So if the way that the arrow points is the direction, and the length is the magnitude. Right? So if these were two planes, the two planes are going in the same direction, but the bottom one is going twice as fast as the top one, or faster, however much faster.
So the length is the speed,
Yep, the length represents the magnitude.
which is just speed.
If you're talking about velocity, it would be speed. If you're talking about like force, it would be how hard something is pushing. Yeah. So in the context of our problems, magnitude is either going to be like the speed, or it could be how hard a force is pushing or pulling. Yep. And then the way to which the arrow points, that's your direction.
Got it.
Now, for now, drawing it's okay, but drawing can take a while because first of all, you need generally a piece of graph paper. You want to try to draw it straight. And if you have rays that are big, they can go off the graph paper. So generally, we don't want to draw for everything. Okay, we want to come up with a faster way. And I'll show you what that is in a little bit. All right, so let's say that we have 2 points. P and Q, like this. In geometry, the way you would label something that goes from P towards Q is just like that.
Yep.
Okay, that's the notation for a ray in geometry. Where the ray starts, that's called the initial point, and where the ray stops, that's the terminal point. Okay, so one difference, when you talk about a ray in geometry, technically, how long is a ray?
It's infinite in one direction. And
Right. It just goes on forever. So that's why I tend to call it an arrow, because I think of an arrow as it stops. If our ray went on, if this was really a ray and it did go on forever, that would represent something traveling infinitely fast.
The terminal point is where you're going.
Yeah,
Always, it's always like the end destination.
yeah.
Okay.
So our rays, our arrows. Question? You're not going to ask me at the end of the week that you're confused, right? Okay, that's probably not going to help you to comprehend it, but
He's gonna like osmosis it in his brain.
That's not.
He has a camera.
That's not.
so when you're looking for the name, that is one way to do it. But there's another way we do it. We just use a single letter to name the vector. The problem is we already use single letters for something else in math. What do we use single letters for?
Variables.
Right, we already use single letters for variables. So there's a difference between a vector and a variable. So you can't just use a single letter. But what you can do is you can use a single letter with an arrow on top. That's one way to name a vector with just a single letter. Or you can make the single letter bold. Bold is what you're probably going to see in our book most of the time.
The arrow's so much better because it shows you like it's the
Yeah, so either notation is correct.
got it.
But that's how you can name a vector as a single letter. Either make it bold or put an arrow on top of it. There are 3 letters that you do not want to use when you're naming vectors. I, J, and K.
Why?
That's because they are special and they mean something. We're going to learn either end of today or tomorrow what they mean.
Okay.
Yeah. Other than that, you can pick any letter besides I, J, and K for the name of the vector. I probably wouldn't pick the letter O,
Why?
because that could look like
Zero.
a 0. You know, lowercase l could look like a 1. You know, I don't know.
So X and Y are the 2 good ones.
You could use X and Y. You'll see M and N a lot.
What about Q,
Q.
W,
Yeah, you'll see W. Yep. W, D.
G?
Any letter except I, J, and K. Yeah. Okay. So let's look at what happens when we add 2 vectors together. So let's say we have a boat out here, and we have wind blowing that way. If that's the only thing happening, what direction is the boat going to go?
Up.
Yeah, on the screen here, the boat would go off the screen. Now, what would happen if we took away that wind, and then we had like a wind blowing this way?
It's gonna go to the right.
The boat would go to the right. Now, what happens if, maybe this, pretend like this was a little boat, and you put like a fan on it. If we put a fan pointing up and to the right,
They go diagonal.
right. In this case, the boat's going to go up and to the right. It's basically going to do this with this,
Wait, what?
and the result is going to be that.
Yeah.
What I just did is I added this vector to this vector visually.
Add vectors?
Yep, to get
Can
the
we
red one.
divide vectors?
No. Nope. So this thing right here, what is that I just created by combining
Hypotenuse.
this one with this one?
Right angle.
Well, it's like kind of like a hypotenuse, but this thing itself is a what?
Arrow.
A vector. This is a vector. So the point is when you combine one vector with another vector,
You get a vector.
you get a new vector. Yep.
How do you like know how to add them?
I'm going to show you that right now. Okay, so when you combine two different vectors together, you get a new vector. The new vector can be longer, could be shorter. In this case, this is longer than both of the originals.
It'd be shorter.
How could it be shorter? Well, if you combined a vector like this with a vector like that, it might end up being shorter because when I connect them, what's happening there is one of them is kind of canceling out the other. So in that case, the green one is shorter. So now I've done this a couple times where I kind of line these up like this, and then I draw that answer in like that. That's what I'm going to explain to you how to do right now. Okay, how to line them up and then connect the diagonal. Yep.
My question was how to do that.
Yep, so now we're going to look at that. So let's say you want to add two vectors, v and w. Just to show you one more time before I write it up. Here's one. Here's the second. If you want to add those two vectors together, you line them up just like that. So you want to position them so the end of one lines up with the beginning of the other. This is the end of the black one. And that's the start of the blue one. Line them up just like that.
But like, what if you had done it the other way?
We'll talk about that in a minute.
Is it different or would it be the same?
It ends up being the same. Yeah. So the other way you could line them up would be like this. That's the only other way you could do it. But it still would come out the same. So you position them so the end of one lines up with the beginning of the start. So the end of one and the beginning of the next. Okay, so let me line some up down here. Here's one, here's two. Okay, once they're lined up, the final answer is going to be what you get when you connect this to that. Just like that. So that would be the result. If there was like a little boat and you put a fan blowing up and to the right, and then you put a fan blowing down and to the right, the boat would pretty much just go straight to the right when you combine those two vectors together. Okay, so the new vector is found by connecting the start point. We'll call this V. And we'll call that W. Connect the initial point of V to the ending point of W.
Wait, the initial point of V is touching W?
That's the initial point of V. So connect the initial point of V
Oh, to draw it? I get it.
to the ending point of W. And drawing it out, if you've got a word problem, drawing it's pretty good because then you can see what's happening. If you're trying to visualize it, drawing it's good. But the problem with drawing is if you have vectors that are big, it can go off the page. Okay, so-
I mean, are they like true to size? Like, why can't they just be like smaller?
Well, I mean, if you have a certain size graph paper and you have to draw something 10 units long, unless you scale your graph paper, I mean, you could, yeah, you could make each block on the graph paper worth 2 or something. But if you don't do that, then your vectors get pretty big. Like if you have to draw a vector 7,000 units long, you definitely want to scale your graph paper or not graph it. Just use the numbers and don't draw it.
How do you use numbers?
We're going to get to that either today or tomorrow.
Okay.
Very end of today or maybe beginning of tomorrow. We'll see. Yep.
Can I run down to the nurse?
Yeah.
Do I need a specific time?
Okay. So let's add V and W together. To combine these two arrows into one, how do I have to position them?
You take the start point of W and put it on the arrow and V.
Yeah. Line it up just like that. That's V plus W. That was V. That was W. Again, that's bold. Just pretend that they're all bold. And once you line them up, how do you get your final answer?
You go from
Connecting the terminals.
You go from the start point of V to W and
Initial point of V to end point of W. There is an arrow, you just can't see it. Now look it up. And that is the answer. That's V plus W. So in this case, it is a picture. That is the answer. You draw a picture. And that is to scale. That's exactly the length that it should be based on those two vectors. Any question on adding those two together? All right, let's look at this one. What do you think is going to happen when we add these together?
Cancel.
Yeah, they're gonna cancel out. So here's the end point of V. Here's the start point of W. You're supposed to line those two blue dots up.
you can't.
Well, you can, right? You can line them up. So once we line them up, then you're going to connect the start point of V to the end point of W. So you're starting here, you're stopping here. So you're supposed to line the blue dots up first, and then connect the green dots.
But it's just a dot.
Right. But then when you line the blue dots up, the green dots also line up. So now when you try to connect them, they're the same point. There's nothing to draw for this picture.
So it's not a vector. It's one.
Well, it is a vector, because remember, when you add two vectors, what do you always get? You always get a new vector, but this is the vector that represents basically canceling out.
Oh, like if two things are blowing at one thing, it might
Yeah.
move.
Yep, or like a tug of war where each side was pulling exactly the same strength, nothing happens. So we call this the zero vector. So you can write the answer like that, or make it a bold zero. That's your answer. It's the vector that represents canceling out. You can't draw this because it has no length to it, and it doesn't point in any direction because
It's not going anywhere.
it's not. It's called the zero vector. So it's kind of a special case. It's the only vector that does not have a direction because everything's canceling out. Yes.
For a problem like this, though, unless it's like the zero vector, would there be like no numbers? It would just be like a picture?
No, you can write vectors with numbers.
How do you?
Okay.
Yeah. So that's eventually what we want to get to after we get through the visual stuff. We want to get away from drawing.
Will we have anything like this on the test, or probably not?
Drawing?
Yeah.
Yes. Yep. There'll be some sketching on the test.
Of vectors?
Mhm.
Okay.
Yep.
From numbers?
From numbers or from pictures?
Are you just gonna be like draw the vector and then just drop some crazy numbers down?
Yeah, you'll see. Yep. So earlier somebody asked about what happens if you switch the order that you add two vectors in.
Yeah.
Well, it turns out it still comes out the same. So let's try that on this one.
But wouldn't the orientation change or no?
No. Nope. So switching the order and getting the same thing means that it is commutative. Right? You might think, well, yeah, when you add, it's always commutative, right? Like 2 plus 5, 5 plus 2, same thing. Well, yeah, that's how numbers work, but these aren't numbers. These are vectors. They're arrows. So can you switch the order of the arrows and have it come out the same? Well, let's see. So here's V, here's W. If I want to do V plus W, that means you put V down and then add W on the end of it. When I do that, this, again, the best I can draw it, that is the answer for V plus W. Just like that. Now I'm going to switch it and do W plus V. That means I'm going to put down W first, and then I'm going to put V on the end, like that. That is a different picture than what I had before. It's W with V on the end. Okay, let's draw the answer. That's W plus V. But if I line them up and compare the two, and I didn't use a grid, so it's not perfect, but you can see they do come out the same.
Yeah.
Okay, so the order that you add two vectors in doesn't make a difference. And it's not just 2. Okay, let's say you had this one, plus this one, plus that one. And you wanted to add, let me draw that a little better. You wanted to add all 3 of those together. Well, you can add as many as you want together. You just keep stacking them up. Let's do black plus green plus blue. So if you want to know what's the effect when you add all 3 of those together, it would look just like, a little off, but kind of like that. Now, instead of doing black, green, blue, let me switch the order. Let's do blue, black, green, and see what happens.
That'll change the magnitude, right?
Blue,
No, you
black, green. Everyone agree that's a different order than I did before?
Yeah.
Okay. But look at the answer this time.
Oh, the magnitude stays the same.
It's exactly the same answer. So you can stack them together any way you want, as long as the arrows are all following a direction. Think of it as it's like a one-way flow. What you can't do is this. You couldn't stack them
Why, it's still one.
like that. That doesn't work.
But what if you do that, what we had before, can you put the green back where it was?
As long as you stack them so the arrowhead is connected to the non-arrowhead.
So that's still, oh, okay.
Arrowhead to non-arrowhead. Yeah.
Is it, but like if the blue and the black are touching, but they're still both connected to the green, no? Or that's not acceptable?
You just can't do arrow to arrow.
Yeah, you just have to connect the end to the start.
Okay.
The blue would be.
I mean, you could do it like that. That's fine.
Yeah, yeah.
Or you could put the green one down here and then put the black one like that. That's fine.
I got you.
They're all of those are going to come out the same.
Believe in yourself.
Yep.
Are we gonna have any word problems that are like, they're going against each other?
I don't think so.
Okay.
No. Okay, and the other property that works with vectors is associative. Okay. Associative, I'm not going to go through this one, but associative, the order is the same. ABC, ABC. What's different is order of operations. Okay. Think of it as like with numbers.
Will you still come out with the same number?
It still comes out exactly the same.
Oh, because addition always will be the same.
So that would be 3 plus 3, which is 6. This would be 1 plus 5, which is 6. You can do exactly the same thing with arrows. It comes out the same. Okay, so commutative property and associative property work for vectors. That's an example of what we just did in this problem right here. When you have 2 vectors that point in opposite directions, and you add them together, that's the answer. It's called the 0 vector. So what's the difference between this and that when you draw them?
One's gonna be
It'd be
pointing
going
the other way.
the other direction.
Right, one of them goes in the other direction. What's the same between them?
The
They
value.
both the same distance.
The same what?
Distance.
Yeah, the length of each arrow is the same. They have the same magnitude. Yep. So when you put a negative in front of a vector, that means the vector points the other way. That's all that a negative does, makes it point the other way. So, what if we had, let's look at something like this. Four minus 2. So, next thing we're going to look at is how do we subtract 2 vectors. Well, as long as we know how to add them, we can subtract them the same way. How could you think of 4 minus 2 as an addition problem?
4 plus -2.
You could think of it as 4 plus the opposite of 2. Everyone agree those are the same thing? That's exactly how we're going to do subtraction with vectors. Instead of subtracting a vector, you're going to add the opposite. Remember what opposite means. You're just going to flip the vector around. So to subtract two vectors, we're not really going to subtract them. We're going to add the opposite. But adding the opposite is subtraction.
Are we gonna be like multiplying vectors?
Not today or tomorrow. Yeah. That'll be Wednesday. No, we might get to that tomorrow. I'm a little off because we're doing the lessons in a different order. But yeah, we might get to that tomorrow.
Can we divide vectors?
No. No, there's no such thing. Okay, so to subtract two vectors, add the opposite of the second one, so you flip it around. All right, so let's do V minus W. Okay. How are we going to think of V minus W? So it's addition instead of subtraction.
V plus negative W.
So what we're going to do is take W, we're going to flip it around, and then we're going to add it onto the end of V. That's how we subtract it. Okay, so visually, we've got V, we've got W. First thing I need is negative W. So on the smartboard, the easiest way for me to do it, I can make a copy of it. If I had a rotate 180, I would do that, but I don't. So I can flip it, and then I can flip it again. And that's an exact copy that's pointing the other way. Okay, so that is negative W. Any questions why that's negative W? All right, now take V and put negative W on the end. What do I have to do now?
Now you draw from the origin point to the terminal point.
Yep, from the start point to the terminal point. And that arrow right there, that is V minus W.
This is fun.
And that's your answer.
I love adding shapes.
This is pretty easy.
Yeah, this is a couple of pretty easy. These couple lessons.
What else are we doing?
Any question on V minus W?
No.
Okay, so that's subtracting. Now, the next thing, somebody mentioned this word earlier, a scalar. So a scalar is just a number. And when you scale a vector, there are three different things that can happen to it. Think about if you make a scale model of like a house. What does that mean?
It's smaller but still proportional.
Yeah, it's still kind of like everything looks the same, but it's a smaller version. So in our case, it's a vector that would point the same way, but be a little bit shorter. What else can happen when you build a scale model besides making a smaller version?
It can be bigger.
It could be bigger, right? If you were building like a model of a
Bug.
like a bug, or yeah, like a maybe an atom or something in chemistry, you might make a bigger model. So when you scale a vector, it can get bigger. And there's one more thing that can happen to a vector if you scale it by a negative number.
Stay the same. Opposite.
Yeah, what would that mean, the opposite?
Inverse.
So what would happen when you draw it?
It'd be backwards.
It points the other way. Yep. So when you scale a vector, it can get longer, it can get shorter, or it can reverse direction. This is what a scalar looks like.
Could I have your attention, please, for a few important announcements?
Okay, so that's an example of what a scalar looks like. It's when you put a number in front of a vector. Okay, so that case, it would mean take the vector v and make it 3 times as long. Yeah. So that is not multiplying a vector times a vector. That's multiplying a number times a vector. We're not doing a vector times a vector today.
So V is for vector.
Yeah, v would stand for a vector. Could be a V or a W or a M. And remember, just no I, J, and K right now. That's something special. Okay, so they gave us a vector. They want us to find 2v and 1/2 v.
So 2V would just be it doubled.
Right.
And then
How could I get it doubled exactly?
You
like that?
add it to itself.
Add it to itself. Okay, so you don't need to measure it. You just put 2 copies of it together.
Is it gonna have us like copy them on the test?
You might have to draw on the test.
Okay.
Yeah. So you put two together and then actually draw the answer. That's 2v. How about 1/2 v?
Half of one.
Yeah, I don't have a way to do a half exact on the board, so that one I just have to estimate.
So you just take the half of it?
So it'd be about like that. So in that case, that's a scalar product that made the vector longer, a scalar product that made the vector shorter. Let's try this one. When I do -1v, is that going to get longer, get shorter? What's going to happen?
It's gonna turn around.
It's going to stay the same length. There's no change to the length,
But the direction will change.
but it will change direction. I'm just going to draw it by hand.
Whee!
We should have a pizza party.
Okay. So that's -v. How about -1/3 v? What are the two things that would happen?
Direction and
It'd
a
be-
third of the length,
So change direction and
a third of the length.
1/3 of the length.
How do you draw it like so that it's absolutely like 1/3 of it?
Well, if I had it on graph paper and like the original was over 6 up 6, this would be like over 2 up 2.
Okay.
So I'd use graph paper. I'm just going to estimate. So I've already flipped it right here. And we'll say that's about -1/3 v. Actually, write it down there.
This is fun.
Okay. Any question on that? All right, so now let's try both together. Let's take a scalar product and do addition at the same time.
Okay.
Okay. What's the first thing that they want me to
You have
find?
to double V.
Okay. Now, both v and w point to the right. So I would start like over in this area, so that way we don't go off the page.
Okay.
So how many of v do we need?
2.
2v. So let's put that there. There's 2v.
Okay.
And then what are we putting on the end of that?
3 W's.
3 of the w's. So make 3 copies of that and put those on the end.
I'm not excited to have to do that.
Okay, so now you've drawn everything you need to get the answer, but now we still need the answer. How do we get that?
We draw between the origin point and the terminal point.
Yeah, from the start point to the terminal point. And that is the answer for 2v plus 3w. Okay, any question on that? Okay. So, if we're going to get away from drawing vectors, we need some symbols to represent what we used to do as a sketch. So we're going to get away from drawing. If you want to represent the length of a vector, the magnitude, you put double bars around it. It's kind of like absolute value, but you need 2.
Is there usually a number on the inside?
Nope, it'd be a vector.
Like an arrow?
Yeah. Yep.
Where is the arrow?
Well, it would be whatever picture goes with V. They didn't give me the picture in this case.
I thought you said there'd be no pictures.
Well, we're starting to get away from pictures. Yeah. So, if you want to represent just the magnitude of a vector, you put those double bars around it.
Which is like how long it is.
That's how long it is. Yep.
So what is 4 lines in length?
Well, that's always the symbol you use. Just
Oh, I
double.
thought that represented how long it was.
No, double bars around the vector.
So how do we, are you going to explain? Yeah.
Yeah. Yep. Now, if the magnitude comes out to 1, that's a special, has a special name. When we talked about a circle with a radius of 1, anybody remember what kind of circle we called it?
Units.
A unit circle.
Unit circle. So what do you think we call a?
Unit vector.
Yep, we call it a unit vector. I think I write that in a second. A unit vector is a vector that has a length of 1. Length is always positive. You can't have negative length. So what would be the difference between that answer if I wrote that down on paper? And that one.
They're the same.
They are exactly the same. Some people say, well, but it points the other way.
But the length is the
The
same.
length is the same. That's what it's asking about. Those two things are exactly the same. And then the last thing I think I write on this page is, yeah, if the magnitude of a vector comes out to exactly 1, that's a unit vector. And that's starting to get at the I, the j, and the k that I mentioned to you. Okay. We are gonna get to I and j today. K we will not get to.
I thought we couldn't use I.
That's
There's
why
a
we use
reason.
I.
Right, we're gonna talk about why we can't use I. We don't want to use it because it means something else. So the book uses it because it means something. But when you're naming a vector, don't use I and j yourself because it already means something else. It's kind of like this symbol in math. Don't use that for anything in math unless you mean 3.14, because it already means something. So in vectors, this means something special, and so does that. And so does k. But k is 3. We're just doing 2D today.
Interesting.
Okay, so if we want to add vectors, subtract vectors, and scale vectors, it would be a lot faster if we could do it without drawing it. Okay, drawing it has a couple disadvantages. One, to do it accurately, we need graph paper. 2, if we add vectors that are big, let's say you have to add 50 of them together, you're either going to go off your paper, or you're going to have to get a bigger paper, or scale your paper. It gets kind of annoying. So another way that we can represent a vector is this notation right there. Our book calls that the algebraic notation, algebraic vector. It looks kind of like a coordinate, but a little bit different. The difference is you're going to have 2 numbers. You will have a comma, but instead of parentheses, they put these like angle brackets. So that is an example of a vector without drawing it as an arrow. So I've got to explain what the 2 and what the 3 mean. Think of the 2 and the 3.
Wait, what's horizontal and vertical mean?
What's horizontal and vertical? So I'm going to show you that right now.
Okay.
We're going to think of the 2 and the 3 in this case as like directions. Let's say you start here. If I asked you to draw that vector starting right there, it means to go 2 units horizontally and 3 units vertically. That's the start
So
point.
would they always be 90?
Yeah, yes. And that's the end point.
What if it's not a vector that's at 90 degrees though?
Well, this would always be a 90.
Yeah, but not all vectors are always at 90.
Well, if you go right and up, or you go right and down, or you go left and up, or
Yeah,
left
I
and
get
down,
that. But not-
you're always going to get a 90.
But we just did a bunch of vectors and they
But it's
weren't
not like
What
90.
he drew isn't a vector. The vector is a point. This is a distance.
Yeah, this is the vector right here.
Oh, I'm thinking about adding vectors, I think, because
Yeah.
I never made a 90 degree.
So it's just like saying you can always make a triangle if you put
Oh,
any
is it
2
kinda like a
points.
slope? Like up, over?
Yeah, it's like kind of like slope. You think of the 2 and the 3 as like the rise
Oh,
and the run.
yeah.
Yeah. Run, rise. Yep. So the 2 and the 3 are like directions. They tell you, this number tells you from the start point how many units left or right you need to go. And this number tells you how many units up or down. So the A tells you left and right, and the B tells you up or down. So let's do something with,
I'm assuming if it's like negative, it just goes down.
negative would be down, yes. Doing okay?
Yeah, my bad, not gonna do that.
All right. So let's draw the vector. I'm going to pick a different one. Let's do 2, 5. 2, 2, 5. So the 2 tells me, that's the horizontal, how far left or right to go.
So up, over 2, up 5.
So let's start here. So over 2. And then the B tells me to go up 5. 2, 1, 2, 3, 4, 5. That is a picture of that vector. Here's another picture. Right, 2, 1, 2, 3, 4, 5. That is also the vector 2, 5. Okay, I could do it over here. 2, 1, 2, 3, 4, 5. These are all the vector 2, 5. What this doesn't tell me is where to start. I can start anywhere that I want. Right, 2, 1, 2, 3, 4, 5. Any of those are correct. The important thing is, if you make a triangle out of it, the bottom side is 2, and the height is 5. 2, 5. If it's not a 2 and it's not a 5, then you didn't draw it right. It has to be 2, 5. If a vector starts at the origin, okay, that's called a position vector. Out of all the different vectors I put up here, that's the most common place to start from. You don't have to. You can start anywhere you want, but that's the most common place.
So negative 2, 5, the vector would be pointing the other way?
Negative 2, 5, that would look like left 2, up 5.
Okay. But you can do that, you can have negatives in the vectors, right?
Yep. Yep. You can have both. If you have one negative, it could go this way, could go this way, or it could go that way. It can point in any direction.
And how do we, it'll say like this is starting at the vertex or what?
Well, if it just said to sketch the vector, you can put it anywhere you want.
But if it's a sketch vector at the vertex, you sketch it at the vertex then?
Well, if it said sketch the vector like as a position vector, then you need to start at the origin.
Okay, position vector starting.
That's the term they would use, yeah, position vector. So let's erase all these other ones. And let's see if we can figure out the position, this vector from this picture. We already know the answer. The answer is 2, 5. But let's pretend that you don't know it's a 2 and a 5. And I want to figure it out based on knowing where it starts and stops. What's the coordinate for this point right here, the start point?
5,
2, 5.
So 5,
5,
5.
5, 5.
So it starts at 5, 5, because here's your origin.
Of the point, I got you.
And what's the coordinates for where it stops?
7,
It's over 2 more.
7, 10.
7, 10. Now, is there something that we could do with those 2 points, and the answer would end up being 2, 5?
subtract them.
Subtract them in what order? Let's call this the first point.
Like subtract x and x and subtract y and y.
Okay, but still in what order?
What do you mean? Like just do x1
P1,
minus.
P2.
P1 minus P2?
Yeah, because P is the origin.
It would have to be P2 minus P1.
It would have to be P2 minus P1.
Is it because of more?
This number minus this number gives you the 5. And 7 minus 5 gives you the 2. If you switch the order, it comes out backwards. 5 minus 7 is not 2. Okay? So it has to be this point minus this one. And what do you, yeah, always. And what do you call this point?
The terminal
Terminal?
minus the original
The initial.
initial.
So terminal minus initial. So let's write that.
So when you're doing it in numbers, that's what you do?
Mm-hmm. So if they give you a terminal point and an initial point and ask you to find the position vector, that's your formula.
Wait, position vector?
It's a position vector.
What does that mean? Again?
It's a vector that starts at the origin.
Isn't that every vector?
No,
Oh,
you can
the
draw a
origin of
vector
graph?
wherever you want. Yeah,
Okay.
you can put a vector anywhere you want.
Oh, I thought we were talking about subtracting. Okay.
Okay, so to figure out a position vector, which is a vector that starts at the origin, if they don't give you a position vector, take your terminal point and subtract your initial point. Do that for the x's, and do it again for the y's.
I was wondering if you could sign a picture of everything.
Can you, yeah, how about, like, you come back at like 2?
Yeah.
Yeah. Okay, so here's a problem, and they want us to find the position vector. Now, if they don't tell you which one is the initial point and which one is the terminal point, you always assume P1 is the initial, P2 is the terminal. Think of P1 as the first, P2 is the second, it's the end. Yeah.
So, this is, I have a question. So say they give you like 7, 5 in there. You could draw it wherever you wanted if it doesn't say position vector. You don't have to start from the origin. You don't have to go
You
like,
do not have to start from the origin.
so you don't have to like count 7 from 0 and then up 5. It could be like 7 from 3
You
on the
can
line.
start anywhere you want. Yep.
Okay.
Yep. And that's exactly what this vector does that I had on the other
Yeah.
page. Somewhere. Yeah, right there. That's
Okay, I
not
didn't
a
know if
position.
like you started there for a reason or no.
Nope. I think I had like 5 different ones up here, and I just erased them all except that one.
Yeah.
Yep. Okay. So let's figure out the position vector. So start with your formula. And okay, so find the position vector. What are you going to put in the 2 spots here to find your x's?
4 minus -1.
4 minus -1.
Wouldn't that just be 4 plus 1?
Yeah, we'll change that.
And then 6 minus 2.
6 minus 2. So what would be
5 and 4.
right? So if you wanted to draw this vector, but you wanted it to start at the origin, you would start at the origin, go 5 units right, 4 units up, and make your arrow. So any question how we use these 2 points to get the position vector?
No. They'll give us the 2 points, right?
They'll give you, yep, and again, if they don't label which one is which, P1 is initial,
Yep.
P2 is terminal. Okay, so I'm going to put up the questions. There's still one more thing I have to do, but it's in a different file, but the homework's in this file, so I'm going to let you copy that first before I open the last. Give you guys a second to copy that, and then I'm going to open up the last thing. All right, so the last thing we're going to look at is what I mentioned about the I and the J, okay, and why we don't use those when we're picking the name of a vector, because they already mean something else. Okay. So remind me one more time, what do you call a vector that has a length of 1?
Unit vector.
Unit vector. Yep. And the last notation that we're going to use to describe vectors is called unit vector notation. Probably the one you're going to see the most on the homework and on the test. I mean, drawing vectors is okay, and that other notation I showed you, it's fine. We use them.
I like that one.
But this is the most common one.
Yay.
So there are 2 special vectors in 2D that have names, and we can't use these names for anything else.
I and K, I and J.
Yep, one of them is I. And when you name a vector I, it means that it is exactly 1 unit long and it points to the right. You can't name a vector I and have it mean anything except that picture right there. If you don't have that, then pick a different letter.
So it's 1 unit long and pointing up?
No, pointing to the right.
Oh,
Please, if we have that vector, but we name it something else, is it wrong?
yes.
If what?
If we make that vector and then we name it like L, is it
No, don't know, it has, it's I. If it points to the right and it's 1 unit long, we have to call it I. Yep. Okay, and the other special unit vector is J. So if you name a vector J, that means that it is 1 unit long and it points up.
Why do they need names?
Just so when we start referring to them, we don't have to draw pictures of them. If we
Are
don't
they
give,
common? Like,
yes, very common. Yeah, if we don't give it a name, then we have to draw it every single time we want to talk about it. Just like every time we want to talk about pi. If we didn't have this symbol, we would have to write 3.14 every single time. But this is short. So J looks exactly like that. It's a vector 1 unit long, and it points up. Okay. Any question on what I and J look like? And when we get to it, K comes out of the board. That's the 3D. That's what's, yeah.
So like with I, right? Does it have to be completely horizontal, or can it be like on a slant but still
No,
facing
it has to
the
be
right?
exactly horizontal.
Okay.
Yep, cannot be on an angle at all.
Also, why do we use I for that? I thought I was like the imaginary number.
So yes, when we do study complex numbers, we do use I to represent imaginary. So I don't know why they use the same letter again here. They probably should have picked something different. But this has not. This is a totally separate thing from imaginary numbers.
And we're not gonna like mix the two at all, are we?
No, no, no.
Alright.
I mean, if they had used, you know, like J, I, and Q or something, then they all would have been different, and those are letters we don't use for other things in math generally. But yeah, I is kind of a repeat. They did reuse it. So the idea is what we're going to do is we're going to take I's and J's, and we're going to stack them together to build our vector. Once you see it, it's very, very straightforward. So think of the I's and J's as like building blocks, like Legos. We can stack them together to make any vector that we want. So let's build the vector 3, 4. When I write it in that notation, where do I have to start from?
The middle. Or
The origin.
Nope.
The initial?
Well, it'll have an initial and a terminal, but where does the
Anywhere.
initial have to be? Anywhere, right? Doesn't matter where I put it. So I'm going to put it there. Right 3, up 4. That is the vector 3, 4. Okay. So now, what I want to do is look at using i's, and if I start stacking i's together, I want to figure out how many I need to get from the initial to the terminal. So, how many i's am I going to need to stack together?
3.
3. So I'm going to make 3 copies of it. Stack them all together.
And then you're gonna need 4 J's.
And by stacking 3 i's together, I just built that vector in red. What is that vector in red? How would you write it?
3i.
3i. That's the first part.
So then
Plus, we need to add something onto the end of it.
do 4
4i.
J's.
4
How many of these do we need?
4
We need 4 of them, and what are they called?
J.
J. I'm not going to copy and paste them this time.
So it'd be 4 J.
1, 2, 3, 4. So this vector that we just made right here is what?
4 J.
4j. And that's the unit vector notation for this vector in black. 3i plus 4j. So notice the difference between the two. If you write it in this notation, you put a comma with angle brackets, and you do not use I and j. If you write it in what's called unit vector notation, you get rid of the comma, you get rid of the angle brackets, and you put in
So
the I
the
and
only
j.
difference between like, will this be like every time where the 3 will always just be you add an I and the 4 will always just be like you add a J? And then
But then you gotta get rid of the comma.
yeah,
and
but
the
like
angle
it's the
bracket.
same base numbers.
Yeah.
And you just, okay.
Yep.
So it'll never be like, say the vector was like 5, 6, it would never be like 9, 12.
No, 5, 6 would be 5i and 4j.
Okay.
Yep. And if we think of that as a right angle, what shape do we have there?
A right
Triangle.
And this bottom side is 3, and that side's 4. How long would this side be?
2, 3, 4, 5.
7?
I'd have to use a calculator. What, 16 plus 9?
What's 16 plus 9?
25?
25.
Squared.
5, yeah. So when we start finding the length of a vector, we're going to use the Pythagorean theorem, which I'm assuming is what you were doing. That's why you square this, and then you add them up.
Together.
Take the square root. Yep. So finding the magnitude of a vector is very easy, as long as you know those two numbers. Okay, so any question on how we built that vector?
No.
Now, if you only use I and j, I points right, j points up. You can only go up and to the right. But what if I wanted to build that vector? Like that.
Negative 1i plus 4j.
Right. Negative 1i, which you can just do negative I. 1, 2, 3, 4j. So by making the i's negative or the j's negative, you can go up, down, left, and right. You can go in any direction you want. Now, what if I wanted to do something like this? How many i's would I need in this case?
Negative 2i.
Negative
No,
1/2.
2i.
2i, because it's 2 to the right,
Plus.
half j.
and negative a half j. So you can use fractions of I and j if you need to get in between. So by using fractions and positives and negatives, you can draw any vector you want in any direction you want.
Will we have to do like a quarter or like a 3/3? Because you have it in the half right now. J.
Not sketching it, probably
Okay.
by hand, yeah. So any question on that?
Will there be any like drawing on the test?
Yes. Yep, there'll be some sketches. Okay, so let me put the homework back up in case anybody didn't get that.